Okay, the quiz from last week is coming around. There's also the mock quiz, which was actually last year's quiz, that I'm passing around as a practice sheet. We've got some business to talk about. We've got some more angle modulation and phase lock loops to get into. And we've got me not feeling very well at all, so I may not last. I may leave. I don't know. We'll see. You guys would either say leave now, or I think it's...
Do whatever you feel.
Yeah, I'm going to do the best I can do. Well, yeah, I thought it was a food infection. I actually visited the doctor this morning, and he was convinced that it's probably what it is, but who knows? I found out when I got here that Dr. Song has been very, very sick. This is what I've heard.
That's why she canceled the day.
Yeah. What's the example of monkey food?
I don't know. They might as well start calling it that soon.
Well, I don't eat on campus at all. I eat pretty good, but I think I might have eaten some fresh vegetable type food that might have been tainted or something. I mean, one little leaf of lettuce could do you in, I think, pretty easily. Okay. We'll get back into the interference. If you got questions on the quiz, you can, I've got the solution posted, but I haven't linked to it yet. I just realized that. What I want to do, though, that's probably more really important to get talking about is just pop up the calendar here. We have a second exam, which I generally would give when we're done with phase lock loops, which probably will be on the 16th. So I would like to give the second exam on the 23rd. That actually is a really good day for me because there's a government TIM with the Air Force. TIM as in technical interchange meeting. I've given you that term before. They use that over at Emergent. And I'm going to be there in the morning and hopefully be done by noon, but that way it'll be easier for me to not be thinking about what my lecture is for that day. So is that votable? I mean, not that you have the final vote, but can we be planning on having that? The idea is to have it far enough along that we don't have a problem with the material and not so far along that it looks like it's coming in at the end of the semester when we're supposed to be having a final. So I don't want to do that either.
Finals week is...
Finals week is way down.
I think it's the 13th or something?
Yeah, and our final is probably either the 14th or the 16th.
It's the 16th.
It's the 16th, okay. The other thing is we have to get another project going. And the second project is generally due during finals week. I haven't gotten the first one graded, as you well know. But, and it will be some digital type modulation related things. Postcode modulation in particular, and maybe something with phase shift keying. I'm not sure. It will have coding theory in it as well. It uses the same audio vectors again, so that you got something to listen to as well. So it takes from speech to digital through a digital pipe with errors, and then taking it back to analog again with errors. So you get to listen to the effects of digital errors, which is different than the interference that you heard before.
Will we know the results of our first project?
Hopefully soon, but you know, when I'm not feeling well, I won't definitely make any promises. I've got 2 papers that are due tomorrow for a workshop. Get those in, hopefully, if I don't get any sicker. And then the good news is I finished getting all of the written stuff corrected for the book, so I just have to do the online supplements. My editor is really happy about that. But I'm not happy because I'm not done yet. I mean, it's like I want to be done. And if you haven't done it, what goes on this weekend? If you're gainfully employed, needing to do important things, you have to do taxes. So I haven't done my taxes yet.
Oh, cut it close.
I always do, though, because if you have to pay, there's no sense in hurrying. So I have to pay. I haven't even bought the software yet, but I'm confident I'll just download it from Amazon and have the latest version and go off and rolling, because I've done it before. So any question? I mean, the project, what I'll do on this last project is I'll up the number of people you can have on the team by 1. So I'll allow teams of 3 just for a little added twist in there. Yeah, exactly. That's exactly. Because of the fact that the final's on a Thursday, I'm not going to give you any more time. If the final would have been on Tuesday, I would have given you till Thursday, but...
Okay, so the project will be due the same day?
Yeah, that's what I'd like to do, because that's, you know, cutting it really short for me, too. Okay. Let's go and look at this interference topic that we really didn't get a chance to spend any time on, and briefly look at it. And the reason why I think it's pretty important to have some idea about what interference does and some basic takeaway concepts is that it's always present. There's barely any environment that you could think of where you don't have interference. I mean, last week when my video failed, I was talking about the bootleg radio station. Well, when I went to school in Upper Michigan, there were virtually no stations around. And one of the things that a station that's not properly licensed is probably going to do is it's probably going to drift around. And if it drifts around at all, like in the FM broadcast band, what's it liable to do? Yeah, land up on somebody else's station, and then they're going to complain, and then they're going to say, oh, this station doesn't even belong here, and go after them. But where I went to school in Upper Michigan, we were on the peninsula of Upper Michigan that sticks out into Lake Superior called the Keweenaw Peninsula, which was where they mined all this copper. And across from that is Thunder Bay, Ontario, a couple hundred miles away across the lake, or 100 miles, I think. We got TV stations from there. The closest commercial FM was down in Marquette, Michigan, which, if any of you were in the Air Force, and it seemed like somebody in here was in the Air Force, not so. There's a base down there at Marquette. So they had FM radio, but we couldn't really receive them very reliably. So no interference, but in general, especially those of you in the comm lab, and I was just doing part of that experiment with the radios last Saturday myself, know that there's lots of FM radio stations. There's not a huge amount of breathing room. So first we'll look at AM. In the simple case of AM, the red spike is just a single tone interferer, just like it's a weak carrier signal or some single spike kind of nearby the carrier for our system, and then the upper and lower sidebands are just there to represent a message signal. So if you take and land that interference term in with the AM in your standard coherent demodulator, it's just going to coherently demodulate everything. So it's going to take that tone down just like it takes the desired tones. Those will get converted down to baseband, and the interference tone will come down as if it were a single sideband term. So it pops in, and you've got the interference. This interference is made stronger or weaker. It either comes or goes, but it's present. Now, one thing you can do to mitigate this interference, can anybody think of what would be the intelligent thing to do? And this is what the superheterodyne receiver, down converters, and all those other things we talked about do. What do? You filter before. So what would you do before you went? You put a bandpass filter. So you put some filter centered right over here. But if the filter is not particularly powerful, like it's got very gradual roll-off, like that, that interference can still get in and cause you some damage. But in the linear receiver, it's just a linear relationship. So the interference just comes in direct proportion to its strength relative to the sidebands of interest. So that's not too bad. At least it's manageable. Now we go on to the envelope detector. The envelope detector is a little bit different to work with. So to work with the envelope detector, what we have to do is go back to this complex envelope idea that we talked about weeks and weeks ago, where we expanded all of the signals with respect to a carrier frequency. So we can already expand, this is already in the complex envelope form. At least we can get it there. We have 1 times AC times a cosine omega c, and then we have AM cosine omega m times a cosine omega c. So what we need to do is just get the interference expanded about that same carrier, and that's using a trig identity. So that's what we have right here in this form. That's just expanding everything about the carrier term, because we're making the assumption that the carrier term is strong compared to the interference. So putting it into a complex sinusoid form, and this is kind of reminiscent, remember when we went through this before, of the phasor addition formula from 2610? That takes you back a long time, I realize, but remember when I talked about that before? How it's related to that? Except for now the coefficients might be time varying. This is, the fundamental concept doesn't really hinge on it once you understand what the result is. So we put it in the complex envelope form, or put it in this complex sinusoids form, and we have everything in this parenthesis is what is like from your phasor addition formula, and then this is the common frequency e to the j omega ct. So we have this complex envelope is what's inside the parentheses, and it's got a real part and an imaginary part, and it's the envelope, which is the magnitude squared of the so-called complex envelope, which is just the square root of the sum of the squares, is what the envelope detector works off of.
Sorry, I didn't quite get what you just said there.
Well, the envelope detector works with the envelope, which is the magnitude of the so-called complex envelope.
Oh, okay.
So what's in parentheses there, up above, I take and form the magnitude of that, which is the square root of the sum of the squares of the real part and the imaginary part.
Now, you said that was derived from the complex, or the
Phasor addition formula, yeah.
AC plus AM, all that stuff.
Mm-hmm. I could scribble that out if anybody wants to see it.
Yeah, I think you should.
Okay. I'm winging it, and in my current condition, I can't guarantee how well it will be. I did put it in as a proof in my book, but I don't think it survived. I actually think it got cut. I'll just take a simple case of two terms. So going back to the phasor addition formula from 2610, this would have just been a constant A1, and this just would have been a constant A2. So in the notation, and I could spice this up a little bit, and I could say, maybe this was J down here, okay, just to make it a little bit more interesting. So from back in 2610, what you said in the phasor addition formula was that x of t was equal to b times cosine omega t, where b was equal to the sum of, well, let's see, it was b, never mind, I've got to do this a little bit differently. It was magnitude of b times cosine omega c t plus the angle of b. And b was the sum of those terms. So it was like a1 plus a2 plus, well, actually I don't need to write it as a sum. I just can write it as ai, where those terms ai could be complex. And I didn't really do a good job here, though, because I put the j in front of the a2. It should have just been a2. Just pull that out of there. Actually, I got this messed up even more. This is where the angle should have been. So you have to add up the magnitude and the phase in these guys. So this would have been things like A1 angle, A1, and these should have been the magnitudes too. But I didn't do it that way. So that same idea, and this is where I'm starting to get fuzzy because I wasn't prepared to actually whip this out. The same idea applies to what we're doing here, except what we're doing here is we don't have an imaginary part or an angle part, we just have purely the real part. So the A1 is just purely the real part. So when we go to find B, in this case it becomes just square root of A1 plus A2 squared plus, and these would be all the real parts, I guess. This is the imaginary parts. That's how we get our envelope then. This would actually be the magnitude of B. Because B is complex, it has a magnitude and a phase. In this case though, because like I said, A1 and A2 are functions of time, we actually carry that right on through, and that's what you saw me doing on the other page. Sorry it's not better than that. I'm just trying to give you the flavor for how it works though, and these two lines in here hopefully remind you a little bit of what you saw in 2610. That's the basic phasor addition formula, and this is just the extension of it to time varying signals. Let's go back and look at the notes, because the punchline is not going to be nearly as thrilling as all the math details, but that's kind of the way it seems to always work out. So then we go to the approximation that we've dealt with earlier, and that is, as long as AC, oops, I get the wrong tool. As long as AC is much greater than AI, then we get to use the binomial expansion, which says that that first term dominates, and the AI sine omega I term is tiny. So the binomial expansion, remember, says that you get out of there just the first term. That's the dominant term that comes out then. That's in the binomial expansion. So you get out, again, a linear relationship. And that's actually, I wrote that down here. The DC is this guy right here, and of course the coupling capacitor or DC blocker would get rid of that. So that's not too bad. The jammer is weak compared to the interference, or compared to the carrier of your desired signal. You're fine. And again, a filter can help protect you against that. But now the tables get turned when all of a sudden the jammer gets really powerful. The jammer is really powerful. Spectrally, what it looks like is That's your AM signal, and your jammer is now like that. That's your interfering signal. So in the envelope detector, that's going to look like your dominant carrier. And those other three spikes, those look like lower sideband terms. So when you go to demodulate that with the envelope detector, it references everything frequency-wise with respect to its offset from that jamming signal. And that's why I said the message signal is lost, because if it was a general message signal like a speech signal, it's just everything's shifted in frequency and it's totally garbaged up.
So when it brings it back to baseband, now that jamming signal is going to be in the center.
It's at DC, yeah, effectively.
Than the actual desired signal.
So they all get shifted off in frequency, and that means they'll get really high pitched if the jammer was far away, or low pitched if it was closer. It'll just be, and there'll be two copies of the message, because you've got each sideband is going to get in there too. It's generally just messed up. So that's what the enemy would want to do to you, right? You might have the filter that has the skirts on it like this to try to cut down on the jammer, but if the jammer comes in really strong, it's still going to be able to rise up above that attenuation of your filter.
So is it so much bigger because it's a single side band? It's kind of like the
I'm just speculating that it's bigger because it happens.
Okay.
And I'm not saying it always happens intentionally, because that's not so. Good example of this, for me at least, is I have an iPod Nano with the FM radio, and we're going to look at the FM interference next, but it's similar. So I'm in the YMCA weight room doing my thing, and along one wall are the TVs. And does anybody know what most TVs in an exercise room have?
Remote?
Besides the remote, what do they usually have? I'm just kind of curious as whether or not you do this. What's that?
Radio.
They generally have an FM wireless to rebroadcast the TV sound. Yeah. If the YMCA has it, the expensive places definitely have it, because I look at the YMCA as being kind of a low-cost workout area. They always have it like 101.1 right on the TV set. So if I'm right underneath one of those TVs with that rebroadcaster on there for the audio, sometimes it wipes out my weak station that I'm listening to. It's gone. On FM, it's just gone. It just gets all fuzzy and splattery sounding. But on AM, it might come in and just kind of do one of these numbers. When I was growing up, because I grew up in the Midwest, the AM radio stations were, out in the cornfields and things like that. They were set up as arrays. Remember I talked about the array patterns and things? Remember that one day? It's not a single tower. It's like a whole array of towers forming a low-frequency array of dipole antennas that are just sticking up out of the ground, and they're phased in order to send their energy in one direction or the other. And you drive past one of those if you're listening to AM radio, and your radio would likely get wiped out unless that's the station you happen to be listening to, because you'd be in the near field, or at least pretty much in the near field. You'd get a very, very strong signal, and it would just overcome your envelope detector. I think the only stations, there's some station around here that has one of those AM antennas, but I can't think where I've seen it. It's out east, though, is where they are. They definitely don't have them on the mountaintop. Does anybody know? Because no one listens to AM radio, so you don't really pay attention to that much. But so it's not bad if it's weak. The main takeaway, it's not bad if it's weak. You can mitigate it if it's weak with the filter, and the combination of the filter and the coherent detector is a very good combination. The envelope detector is just vulnerable, period. But why did we use the envelope detector? It was low cost. It was a cheap implementation. If you were needing really good jamming protection or unintentional interference, you'd probably go with a higher cost receiver, and you just have yourself covered that way.
Did you not use a notch filter at all?
Yes, and that's done too. But then you'd have to have a tunable notch filter, perhaps, if the jammer or interference moves around, and those are also done.
You kind of have to know where the jamming is going to be.
Yeah, and that's done with some spectral analysis. So you'd have spectrum analysis done in your receiver, then you tune a notch, and that's done. That sort of stuff is done in military applications. So, you know, there's measures, and then there's countermeasures, and then there's countermeasures. You've heard of that before, probably. It's an escalation of stuff. If it's unintentional jamming, then you have to learn to live with it, or you have the FCC, you know, put down some laws that basically say you cannot do this. And the project I worked on last year for emergent, there's frequencies that are used to talk to the satellites from ground stations, and then there's frequencies that the TV operators use, and they're rather close to each other. You know, the remotes that TVs do where they have the microwave set up, those things are close to getting interfering with each other. So that was one of the things that we talked about frequently. Okay, in angle modulation, it's a little bit different. In an angle modulation, start off with an unmodulated carrier. Just don't put any FM or PM on it, but then suppose the jammer is offset by some omega I away. Go to the envelope analysis again. Expand the envelope out just like we did before for the interference. Except now we're going to focus on not only the envelope R of T, but also the angle. And of course, why would we focus on the angle for angle modulation?
Kind of on that angle, it's going to affect the messaging.
Exactly, because that's where the message is. It's in the angle. So we look at it in terms of the angle. So if we expand this out, we don't have any message on the carrier right now, but we do have this interfering tone coming through. So we look at the angle, and we see that, sure enough, there is, in the angle of the envelope, as opposed to the magnitude, we do have our jammer, and as long as AI is small compared to AC, this arctangent is just going to let through the interference. And here I'm just using, rather than the binomial expansion, I'm using the power series expansion for arctangent, which is this guy. And if we put it back together as the envelope, which had some fluctuations due to the interference, and the angle of this unmodulated carrier, and then consider how a discriminator might work, where the discriminator would come along, possibly in one of our discriminator designs. Remember, you limit the signal. So if you limit the signal, remember, if you hard limit the signal, that fluctuation goes away, but you still have this buried inside of the cosine from the interference. So if it's a phase modulator, it's going to get the interfering signal back, and if it's a frequency modulator, it's going to get the interfering signal back too. And the thing about getting the interfering signal back in the case of the frequency modulation signal, it also gets a gain that's proportional to the frequency of the interference. And that comes about from the derivative operation that goes on with the discriminator. So that's actually a very important fact. When you have interference in an angle modulated system, the FM demodulator will get a tone, gets the interfering tone back, but it also gets it proportional to the amplitude of the offset frequency. And that seems almost bizarre. The further away it is, the more powerful it is. But that's what the analysis says. I mean, it's within limits because, again, that front end or IF filter is going to have skirts on it, so the signal is going to eventually go away. But when it's in band, it will in the bandwidth of the filter, it will come out with that proportionality. The other thing is that if AI is larger than AC, then the analysis that we just went through with the power series for the arctangent fails, but you can come back to and just say, well, if AI is large compared to AC, in this equation right here, this thing kind of goes chaotic, because now the denominator is got a large fluctuation on top of that AC, and you've got basically a sine over a cosine, which is a tangent, and then you're taking the arctangent of that, so you're being dominated by the interference. But I did some pictures of this in Mathematica just to see what it looks like. This is the case of an interference coming along with the desired signal, and as you bring the amplitude up of the interference, which is what I'm doing here, it starts to, it just gets, like I said, chaotic looking. It gets to looking really bad, and that's the type of thing that I hear when I get my iPod too close to the FM transmitter in the gym. But you could do this in the lab if you wanted to. If you had an FM radio and just put up a carrier that was powerful, it would eventually start producing some strange interference effects. You don't really necessarily hear the tone at first. You just hear sort of the cutting up, clicking sound. Have you heard that before? Yeah. Okay. FM radios actually have what's called a capture effect. So they tend to capture the more powerful signal, but right when they're at the balance point, you'd definitely hear the clicking. But for most of us, if we were listening to an FM radio station when you come over Monument Hill, that's where the capture effect is very noticeable too. First, the signal is Denver, and then maybe momentarily as you're approaching the hill from the north side, it'll flip to Colorado Springs, but then it'll flip-flop like that. Have any of you experienced that? 1 second it's this station, the next one it's the other one. It tends to flip-flop, but sometimes it'll just stay hovering, and then it's like, I can't listen to this because it's schizophrenic. It's jumping back and forth. Eventually, as you get, as that dividing line changes, you're strong on one, and you rarely would hear the other one. Unless you're going east, let's say. If I'm listening to a Colorado Springs station driving on Highway 94 to Kansas, which I have done to get my son, then the stations just fade out. But the capture effect is still present. I mean, the signal's there, it gets a little bit fuzzy, it's still okay, then all of a sudden, it's gone. Then it comes back again. Then it's gone. And then pretty soon it's gone most of the time. So if there's nothing else there, the capture effect just makes it turn to noise. So those are interesting behaviors about FM and AM. AM tends to be better as the signal fades out because it just gradually goes away. FM, because of that capturing effect, it's either there or not there. Yeah.
So when does the interference we're looking at here get introduced? Does it get introduced before the modulation, or?
It gets introduced in the channel. So the signal is up and being transmitted intentionally by that transmitter. You're sitting out here, but there's another source out in space somewhere that's got some interference. It might be in the lab because we've got some test equipment. Like I said, it might be a nearby station that you're, if you live close to that, you could deal with that all the time. Or it could be, in the military scenario, just measures and countermeasures that go on. Okay, one of the things, though, we learned about FM in particular was that the interference grows stronger as its difference frequency gets higher, as long as the signal's in band. So this phenomena was noticed a long, long time ago with FM broadcasting. And it's something you hear when you're listening to an FM radio station. When you tune between stations, you hear all of that noise. And I don't know if you ever noticed, but the noise tends to be, almost sounds like it's more high frequency oriented than it is low frequency. It's got a really hissing sound to it, or high pitched hissing sound to it. And that's because the discriminator naturally emphasizes the high frequency noise more than the low frequency noise because of this differentiation operation, which puts that scaling factor on there. You know, we saw that the gain scales up like that. The AI went up linearly as Fi moved up. In a power sense, it moves up as the square of that, so it moves up parabolically. That's just another fact. That's actually talked about in chapter 6 or something of the book. It's a chapter that we don't teach from anymore. But so one of the things that was developed a long time ago is this concept called pre-emphasis. Knowing that you're going to have more noise in the background for the high frequency components of the modulation when you're doing FM demodulation than for low frequency, you purposefully boost the high frequencies. So it's called pre-emphasis. And it's this bullet right here. So the blue line in this figure shows you what happens to the noise level. Well, it's the discriminator output without pre-emphasis, noise level, and then with pre-emphasis, you're able to apply a filter at the receiver to eliminate that high-frequency noise. The only way you can apply the filter at the receiver without eliminating the high-frequency content of your message is to purposefully boost it up when it gets transmitted. This is an even more foreign concept the younger you are, because you don't listen to records or any media that you know about any emphasis, pre-emphasis stuff going on. But records, vinyl records had the same problem. So they had to pre-emphasize the high frequencies, so they were recorded with the high frequencies emphasized, and when you play them back, you have to put in a low-pass filter to turn down the high frequencies, unless you like listening to lots of treble sounds on your music.
So is that to ensure that AC is much greater than AI?
Yeah, it really has nothing to do with that in this case. Yeah. It's just the fact that the noise in FM, because it has to do with the differentiation operation in FM, takes the noise that comes in and effectively, along with the signal, when it differentiates it, it puts on that emphasis and emphasizes the high frequency noise more than the low frequency. So to beat that out, you put your signal high further up, and then it's above the noise, and then you take both of them down together with the low-pass filter, and now the noise is dropped to be consistent with the noise at the low frequencies, and you maintain good signal-to-noise ratio across all frequencies. And these are the two filters. This is what they look like then. It had two breakpoints in the pre-emphasis filter, just because you don't want to keep, in the design of this filter, you don't want to keep jacking up basically the amplitude of frequencies way up high above your hearing and just put too much high frequency junk into the modulator, so you flatten it out at F2. But F2 is not at a frequency that we care about, because we don't hear at 30 kilohertz, for example. And then at the receiver, you just have a low-pass filter that cuts off at 2.1 kilohertz. And so the time constant of that is 75 microseconds, and that is the standard. And it's still the standard. I mean, that's what's used in FM broadcasting to this day. It's old-fashioned, though, and you can say it looks old-fashioned because it has real circuits in it. It doesn't have digital signal processing algorithms.
So yeah, you said this is old-fashioned. So this technique is still implemented today?
Because we have legacy standards.
Okay.
I mean, it would even be present in certain types of voice communications, although most narrow-band FM applications wouldn't need it because they're narrow-band. They don't have that much deviation. But in FM broadcasting, for sure. Okay, phase lock loops, we started to talk about these last time. The phase lock loop has a number of practical applications. It has applications that are just simply amazing in terms of what we have in our electronics devices today. This is by no means something that's old-fashioned and no one cares about it. It's extremely contemporary to deal with phase-lock loops. So the basic phase-lock loop has these main elements in it. It has a phase detector, a loop filter, sometimes combined with a loop amplifier, and then a voltage-controlled oscillator. Now all of this can be done in analog circuitry. It can be done partially in analog and digital, and it can be done purely in digital, as in digital signal processing, or just combinational logic. It can be done that way too, with flip-flops and gates and things. The approach taken here is all analog, but systems I've worked on, are usually hybrids, or a lot of today's designs will have a digital phase detector, and in radios and things they'll have an analog loop filter and an analog voltage-controlled oscillator. That's the type of setup you'd find in your cell phone typically. How does your cell phone know how to select different frequencies? It has what's called a frequency synthesizer, and how does a frequency synthesizer work? It's a phase-lock loop. So it can tune all those different cell frequencies based on the assignment that it gets from the base station. I mean, you have no interaction with that, but the base station tells your cell phone, when you make a call, we're going to put this person on this channel, because that's the assignment that person gets, and so on. If it's GSM, if it's CDMA, then it's done with the spreading code. But still, you operate in different bands in different parts of the country, so it switches, and it uses synthesizers to switch that. So the basic design for the phase detector is a multiplier. There's other types using digital gates and things, like I said, but a simple idea is just a simple multiplier. So we have two signals we want to multiply together. And like I was telling you last week, it seems like forever, but it's been a week ago, the first thing that the phase-lock loop wants to do is get the frequency of the VCO, get the frequency coming out of here to match this frequency. Once it brings those frequencies into alignment, then it gets the phases into alignment, or at least to within a small fraction of a cycle of phase error. The amount of phase error then comes out of here, and then this acts as a feedback control system. So if the phase error starts to get bigger, it gets gained up by the loop filter and the loop amplifier, and then the input to the VCO over here, what's it going to do? If it gets a higher voltage, it's going to make the VCO tune higher, and it's going to try to follow the input signal's frequency. And then if it's too high, because the phase detector is now putting out a negative control signal through the loop filter and loop amplifier, then it tells the VCO, it commands it basically, because it's a control system, commands it to go lower to keep up with it. But there's time constants, because the loop filter has poles and zeros in it. The VCO is not necessarily having any poles and zeros in it, but any piece of electronics you make always has something that you probably don't talk about too much in electronics, but can anybody guess what do all electronic circuits have that you don't even know are there on purpose, but you have to cope with? It starts with a P. Yeah, parasitic capacitance, and inductance too. A little resistor with a wire on it, it's got both capacitance, parasitic-wise, and inductance. So you deal with both of those. And in high-frequency oscillators, they're there, and those parasitics put in added challenges. So the loop filter actually has to be there to help set time constants, so that the time constants of the VCO and the phase detector don't dominate. And those of you that have taken control systems know what happens when you have time constants that sort of are spurious like that. They will make your system go unstable, because they're kind of like not reined in properly. Whereas by setting the loop filter up properly, then you can control the effects of your parasitics. On a first cut pass, though, you pretend they're not there. So right now we're going to pretend there's no parasitics and not worry about that stuff. So we have a phase detector, and the thing about the phase-lock loop is that it will lock in quadrature. So when it locks up, the relationship is one signal is cosine, the other signal is sine. And to see why that is, all we have to do is use the setup I'm using. I'm supposing the input signal comes in on a cosine, and it's got a phase of phi. The VCO is putting out a sine, and it's got an excess phase of theta. When you go through the phase detector, it produces the sum and difference. We only care about the difference frequency, and we also assume that there's an inverting operation, so because the trig identity here has a negative sign in it. But at any rate, you're going to get a sign of the phase difference, and that's the beautiful thing we're looking for from a control system standpoint. When phi and theta are approximately equal to each other, this function puts out 0. So from a control system standpoint, the sweet spot of operation is right there about 0, where the phase detector, the sign of that angle difference is approximately the angle difference. And then those constants are just gain constants that you carry around to model the phase locked loop. Does that make sense?
So you want it to be that condition? Or
We want to have a function that passes through 0 when the phases are matching each other, because that's the lock condition. When the phase of the input matches the phase of the VCO, and then it can just track that. So theta of t can follow phi of t. That's the desirable, and that's the closed loop characteristic that we're looking for. That's what makes it a phase locked loop.
Does it continually loop until it gets that?
It will settle. Yeah, I'll show you a simulation where it will settle. It won't always start off at 0. And if you put a certain type of input into the phase lock loop, it will always be struggling to keep up with it. And that has to do with the order of the phase lock loop. I think I asked how many people took control systems in here, and I know at least several of you did, right? Kelsey took it. Who else took it? Just 2 of you did? Okay. So I can say things to you guys, and you'll remember more from your class, where the rest of you haven't had it yet. You might want to take it, though. The bottom line is that certain types of a higher order system can track higher order waveform characteristics. And in a phase lock loop, it's things like platform dynamics that we care about. How much Doppler rate, which is acceleration, and then there's another one beyond acceleration. You know what that one's called?
How long is this loop supposed to last?
Loop?
This loop?
It's a feedback loop, so it runs forever once you turn it on. The next higher order, though, is called jerk, right? That's actually the name for it. But satellites, when they're orbiting around, they have components of, they have Doppler, because the range out to the satellite is doing this, and then the rate at which it does is the acceleration, and then it can have, the next derivative, the jerk component, too. The first 2 are the most important, though, the Doppler and the Doppler rate. Okay, question?
You wouldn't want it to go completely to 0, though, would you?
Yeah, you would.
Because then it wouldn't be able to keep going through the system, and you wouldn't end up with any output.
Now, look at it this way. If the output E of D can go to 0, then you don't have to do anything over here. Then you have 0 phase error, which will be great for demodulation. And the way you can still produce a voltage here. And the way you can do that is with an integral. So if there's an integrator in that loop filter, even though the VCO has to tune somewhere other than its quiescent frequency to match the input frequency, it can get to that voltage, it can get that needed voltage at its input through an integrator that's in the loop filter, even though the input to the integrator is now 0, because you've integrated a constant for a brief period and then got yourself biased. And you're good. That's a control system thing, though.
So it can go to 0 momentarily, but you don't want to stay at 0 because you wouldn't be able to
Produce a bias that can move the VCO. Is that what you're thinking?
Well, I guess I was just figuring that 0 is your, I mean, even if you have an integrator in there, 0 integrated over a long period of time is still 0.
But you had a small transient, though, that occurred when something changed, like you switched the input from one frequency to another frequency. A small transient occurs in the loop, and that's enough for the integrator to integrate that and then produce that bias that will push the VCO high or low, and it will hang there. Right? It can just hang out there.
Right, but wouldn't the transient eventually die off and you have...
The transient dies away, but the integral, I mean, an integrator, if it's true to form, once you integrate something, it just hangs at that constant.
Oh, so it's...
I realize in electronics, you think of an integrator built with an op-amp, and what does it typically do? There's a bias current or offset voltage in the op-amp that generally makes it... Don't you do an integrator in electronics somewhere where you put a capacitor across the output back to the input and a resistor?
Yeah.
If you just do that and tie the input and then look at the output, what does it do? It drives off, though, doesn't it? Because there's an offset current and an offset voltage on the op-amp. Like the other terminal of the op-amp, you have to do some tweaking on it to make sure it doesn't drive it off.
So it's integrating over all time? It's not integrating over a period? Or
It's integrating over all time.
Oh, okay, that makes sense.
Yeah.
I'm just thinking that eventually you wouldn't have your input to your VCO would be 0 or whatever.
Now, this is a little bit mysterious, though, and we're going to get into the S domain here eventually, too. I'm just trying to establish the first order loop, though. So we have an output that's a function of the sign of the phase difference. And that blue thing that I drew up there is, because it looks a little bit like an S, it's usually called the S curve for a phase lock loop. It's the transfer function. You want to operate about 0 where it's nice and linear, but that shape is called an S curve. Now we go to the voltage controlled oscillator block. We talked about this earlier as an FM modulator, and that's the exact relationship. The output has got a frequency omega naught, that's the quiescent. It's like you built an oscillator and it has some tank circuit in it, and it sits and operates at that frequency omega naught, but then you've got maybe a varactor diode, a variable capacitance diode, that is configured in with a control voltage so that you can change that capacitance and move the oscillator frequency higher or lower. Or maybe it's some other type of tuning mechanism. But at any rate, that makes the frequency be proportional to the control voltage. So I've got that d theta dt there to represent a frequency offset, because differentiate phase and you get frequency, right, in radians per second. So it produces an output that's at frequency omega naught and has instantaneous frequency of d theta. So it has a phase of theta if you integrate that back out again. So this is the nominal relationship, just not worrying about the quiescent frequency. That's the nominal relationship for input and output of the VCO. Or if you integrate both sides, it just says that the phase at the output of the VCO is kV, which is the deviation constant, times the integral of the control voltage. So if we put this all together with the sign as making the loop nonlinear, we have the amplifier, we have a possible loop filter, but for right now I'm just going to tie a short across there and just make the loop filter go away. A gain mu, and then we have this integral. So there's our feedback control system.
So that's just a more detailed version?
Yeah, well, this would be called a baseband model.
Okay.
Why is it called baseband? Because the center frequency is not in here anymore. It's just been voided out. We're just looking at it abstracted in terms of the phases of the signals coming in. You know, originally it was whatever I called this, A cosine plus theta, or phi, I guess it was on the input. But I'm just looking at the phase of the input signal, and the phase of the VCO is theta. In a computer model and on paper we can do that. In the physical world you can't do that, because you can't actually go in on a time domain signal and say, all I want is the phase out of there. It's like, I just can't, it's like you're trying to grab it and you can't, because you'd need a phase detector or something to actually do that. But now we've also replaced that multiplier by the differencing circuit, which is what the trig identity did on the difference term. It just differenced the arguments. So we got a phi and a theta. In the sum term that was in there, you didn't say, but I noted on the bullets that you just assume a low-pass filter takes that away, just removes the double frequency term. So now if you sum up or multiply out all the gains, you get the total gain, KT, and the VCO output is now going to be theta of KT times the integral of the difference between the two angles. So what we have right now is known as a first-order nonlinear differential equation, where the nonlinearity is the sine function. It's a nasty little differential equation, actually, which we're going to simplify to a linear differential equation in a second, but initially I just want to let you see what it's like in the full form. It becomes a linear first-order equation if you take sine of the angle difference and just replace it by the angle difference. Then it's a whole different ball game, and it's a whole lot easier to work with. But in the lab, when you play with the phase lock loop, you'll be playing with this sort of a model, so you will have these characters. So suppose we give the input a frequency step. So in other words, phi dt has a step of delta of omega. And then we plug that in. So what I did here, what I did on this line right here, in order to write that, I basically said, okay, we've got d psi dt equals d phi dt plus or minus d theta of t. So I rearranged things and I put the d theta on this side, and then I have the d psi of t, which plugs in down here. That has the step on it, delta of omega, and then I move this to the other side, and that has the minus on it. And I know from the original equation up here that d theta of t was that. So now I can focus on just this piece right here and do what's called a phase plane plot. Now, I don't know about you, because I've had differential equations a whole lot longer ago than you did, but can you remember doing phase plane plots in differential equations? No? I vaguely remember doing it, but not very well. The phase plane plot is an idea that is trying to get you to understand what solves this nonlinear differential equation, what makes it happy, what makes it have its solution. So in this case, it will be happy if d psi dt is equal to 0. That's what it's striving for. So when d psi dt is equal to 0, so we have no frequency error in the loop. So if we in this blue curve is a plot of this function up above, it's called it's the phase plane plot. It's basically plotting that out. It's plotting d psi dt versus psi of t. So when the loop starts out, if delta of omega is set equal to 0, we'll be sitting right here, and everything is all well and fine. We have 0 phase error, 0 frequency error. But if we now put in bump the frequency to delta of omega, the whole phase plane plot shifts up like that, just like the equation up above says. And now we're sitting at location B, and now the differential equation starts having to do something as a function of time because it's basically unhappy. It says I've got to get back to 0 again for the d psi dt. So the analysis I have down here says, since time is positive, if d psi dt is greater than 0, then d psi, which is small steps along the psi axis, has to go positive. So that's why I'm showing it going in this direction, because it wants to drive towards 0. Is that making sense? This is a difficult concept. You may have to go back and look at this again, because I have to look at it every time I teach it, like, how do I explain this? If, on the other hand, if we happen to be sitting right over here, like we overshot that stopping point, then since dt is still positive and d psi dt was slightly negative, then in order to be happy it would have to pull back in that direction. So it's got like an attraction force, like a magnet, you know, two opposite poles, they would snap together like that. So in terms of the way this phase plane plot works is points either side of that stable point A are arrived at from either side, and they'll come together and they'll just stop right there because it'll be happy. So the natural question is, what happens if you're sitting over here or sitting over here? Can it drive to this point right here and be happy? It does have d psi dt equal to 0, but from the arguments right here, for example, if it's sitting right on the positive d psi dt, it's like repelling magnets. It's going to say, I can't go there. Instead it's going to zoom all the way around here and get to that. Or if it's sitting over here, it's going to zoom backwards like that and get to the next stable lock point. You know, there's another lock point. There's periodic lock points all along here. It's pretty cool, actually, if you like the math behind it. So a phase lock loop has multiple lock points, and if it has to do an operation like that, it's called a cycle slip. So if it gets bumped really hard, it would slip a cycle or two and then relock again. I think you can relate to that from certain things, like maybe if you're riding a bike and you get, I don't know, I'm trying to make an analogy, something where you get into a pattern but you get jolted by something and you lose that pattern and then you get it back again. Maybe bike riding isn't quite it, but I know on a really windy day, if I get a huge gust, I'm running sideways to the wind that just about knocks you off your bike, you kind of almost are going to crash. You got to get your bounce back again. So frequency area is always 0, but in the first order loop, unlike the higher order loops, you're going to have what's called some static phase error, and that's what's shown in this picture. There's a certain amount of error that comes out of the phase detector because there's no integrator in the phase lock loop, and what that error does, I can get this back, and it's just messed up on me and went back to page 1. So if there's a small amount of error coming right out here, if that's small, what we can think of what's happening is that's coming around through the loop amplifier and it's creating a bias voltage to actually be able to drive the VCO to match the input signal, positive or negative, because there's no integrator in the loop filter itself. And I think that makes sense from no knowledge of control systems, that if you want the error to be 0, you're going to have to create a bias voltage somewhere that's going to push the VCO to match frequencies. So now I guess I had to run a little simulation and then maybe still try to talk about the quiz, because we're going to get into the linear analysis with the S domain here, but we'll have to wait on that. Just go to a MATLAB simulation, and this is available on the website. It's a function called PLL1, which is similar to one of the functions that's in the book. So what I've got with this function is I can put in first order or second order loops. I can put in a loop gain, and if it's a second order loop, I can put in a damping factor as well, and we'll get into that next week. But here I've got a first order loop, and I'm going to put in as an input phase, which I called phi. I'm going to put in a frequency of 5 hertz. It turns on at 0.25 seconds. So if you notice here, I've got 2 pi radians times 5, so that's 5 hertz in radians. And then I've got t minus 0.25, and then a step function that turns on at t is equal to 0.25. Oops. So, did that wrong, but then I'll go into my phase lock loop function, and I'm running a first order loop here. I'm sampling at 10,000 samples per second, and I'm setting the natural frequency, which we'll talk about next time, but basically I'm setting the loop gain to 10. So the loop can track signals up to its loop gain, which is 10 hertz in this case. So if I go plot the output error voltage, we'll see that the VCO error voltage was sitting at 0 volts because it was happy to track the input signal, which was not ramping, didn't take on a frequency offset up to 0.25 seconds. But then when that step or phase ramp turned on, phase ramp being a frequency step now of 5 hertz, the phase error came up in this second order loop, just like that picture showed. It created a small bias which got amplified by 10 to produce a VCO control voltage of 5, and now the loop is again stable. It's locked to a 5 hertz signal that's a signal that's offset by 5 hertz, and it's following it just fine.
That's voltage though?
That's like voltage, yeah. And if I go look at the phase error, which I can look at here, I will see that it's putting out a small value because it's going to get amplified. Actually, if I take the cosine of that, or the sine of that, that's the total voltage that's coming out through the nonlinearity. It's exactly 0.5. And that's the phase error that comes out of my sinusoidal phase detector, and that's what's driving the VCO to make the VCO push to 5 hertz to match frequencies. Now this phase detector, being a sinusoid, can only put out 1 volt maximum because it's the output of a sinusoid is just plus to minus 1. So if I said the maximum frequency or the loop gain was 10, I'm just going to show you what happens if I put in, say, 12 hertz. If I set that 5 to 12, I'll plot the output first off. Well, I'll plot the error, sine of the error. Now what happens is the loop is very ticked off, basically. It cannot match. The VCO cannot get enough voltage into it because the phase detector can't go high enough to drive the VCO to match 12 hertz. And it's trying. It's trying. If we were to go back over to, let's see, the notes over here, if they'll cooperate for me. What's happened is this whole sinusoid has now been pushed up above the line dt is equal to 0. Okay, so it's like the 0 line is down below here. And so now what's the loop doing? It's just continuing to slide along like that. It's hoping and hoping it's going to cross through 0. It's never going to happen. So it just continues to slip cycles like that for forever.
Because when you change the VCO frequency, it's the 12 hertz is too high?
Yeah, I applied at the input 12 hertz, and the phase detector can't put out enough control signal to drive the VCO to match it. So it's just, it can't get there.
That's the input you're driving. 12 hertz is like your XR.
Yeah, that's what I'm putting into the phase lock loop. Now, one application of phase lock loops is coherent demodulation, trying to get a coherent carrier at the receiver. And in this case, if this loop was trying to do that, it would fail to do that. That's about all I wanted to show on that. Wish I could say I was feeling great, but I'm not. So I guess I should go on and look at the quiz. This probably won't show up on a quiz, but it will probably show up, these types of problems will show up on the exam. So these problems all boil down to the equations we were talking about last week, and that is Carson's rule. So we had from Carson's rule there were two forms to Carson's rule. One was the bandwidth of the modulated signal was 2 times d plus 1 times w, and the other form was 2 times delta f plus w. Remember what d was? D was the deviation ratio. So d was delta f over w. W is the message bandwidth. So W here is the message bandwidth, and this is the RF bandwidth. So this is pretty much all you need to know to work these parts A, B, and C. So in the first part it says the peak frequency deviation imparted by the message is 60 kilohertz, and we know that the message has got a bandwidth of 20 kilohertz. So what's B going to be? Take your pick on which formula you want to use. This looks like it fits the second one, right? So if I use the second one, I would say delta F, its peak deviation is 60 kilohertz, and then W was 20 kilohertz. So that would be the answer. That would be 160. Is that right? 80 kilohertz times 2. So that'd be the approximate bandwidth occupied by that signal. The second one is just a variation on that. Yeah, if you didn't come in early, you didn't get one of these samples. So how do you want to work the second one?
Using D, well, it's the same one, but you're multiplying with D.
Okay. So Tim is suggesting just taking the FD, which is the constant in the modulator, times the peak or amplitude of M of t and getting delta F from that, right? Okay, so delta F inferred from the info is 2 times the 100 E3, and then you could go back to the same equation and plug in what you've got. You've got 200 E3 plus 20 E3 is equal to whatever that is. 220, so 440. Is that right? Now the third one, now, or C, you're given the deviation ratio. And remember from the definition, the deviation ratio is the peak over the bandwidth. So that's already set up for the first formulation. So there it's just going to be the 100 plus the 20. Well, excuse me, 100 plus 1, I mean, times W, which is 20 E3. So I've got to do the decimal points in my head on that one. Yeah, 202, 404, Am I missing something in there? There's an extra 0 in there, so it's... Yeah, I'm kind of not feeling great, but does anybody have their calculator, or is their brain working faster than mine is?
40.4
Okay.
megahertz.
Is it megahertz? 2E4, 5, yeah, you're right. That's fat. Fat spectrum, I mean a big one. When I say fat, I mean it's using lots of bandwidth, that signal is. It's living high or something. Okay, the second problem is you can just get from the discussion in the notes. What I would like you to do, though, is look at this homework problem. You still need to look at that? I want to go look at one of the homework problems that I did not put the solutions on here, but I did not get synthesizers in here. We'll be talking about that next week. But this problem, number 1 problem, is an interesting problem. And if I was to pose you a word problem like that on an exam, hopefully you'd be able to just steadfastly work through it and not get confused, because it has fallacy in there. He or she gets confused, and so I have the solution for that one posted, but I took this from another book a long time ago. I just read through it and then see if you can make sense out of it. I just suggest you go look at the solution, or just work through it first and then see if you agree. I made it. I just got to get home.
Get some rest. Have a good weekend.
Interesting thing that's come up for